Professor, can you hear me?
Yeah, Ivan, can you hear me okay?
Yes.
Awesome, thank you. All right, so let me just adjust my papers here. All right, good morning, everybody. Hope you're doing well. Couple quick announcements and reminders before we get started. So as a reminder, Thursday is Veterans Day, so there's no classes on Thursday for this class or any Thursday classes. So we will not be meeting on that day. In terms of your mini quizzes this week, you have 2 still on Wednesday. You have global maximums and minimums, which we're going to cover today. And then for Sunday, you have marginal cost and revenue, which we started last class and we will also finish up today, which is not a super long application because most of the applications actually go back to the stuff we learned about economics in chapters 1 and 2. So you may need to reference those notes for some of the work you'll be doing in that section. Other than that, I think that's all. So after class today, I won't see you guys again until next week on Tuesday. But otherwise, things are sort of plugging along as we go. So let's see. So we're a little out of order, but I think this makes the most sense. So we have one more example we need to do from marginal costs and revenue as applied to maximums and minimums and thinking about how those things are related. We started this last time, and so we'll finish up with the last example there, and then we'll switch over to global maxes and mins. So I'm going to go ahead and switch over to the dot cam. Okay, and actually, really quickly, just as a reminder of what we were talking about last time in our definitions, we're looking at how cost, revenue, and profit and marginal cost, revenue, and profit are related to what we're doing now, which is just maximums and minimums. So here we looked at how to set that up, what that might look like. And so our sort of other big problem that comes up here is this problem that comes up about trying to maximize revenue. And so this particular problem has several steps to it. And one of the things I want to point out is that this is a problem that comes up often. I think it's on homework and it may be on your quiz. And this problem is set up to show you all the steps to do it. But when you do this on homework or the quiz, it may just ask you to do part C, find the price and quantity, which we'll talk about in a second. But you still have to do parts A and B to get to part C. Okay, so here's the situation. A theater has 1,000 seats. And when they set their ticket price to $10 per ticket, the theater sells out. For each additional dollar charged, the number of seats purchased is reduced by 50, right? So we want to start by finding a linear equation that fits this data. So when we do this, we want to just find something in the form y equals mx plus b. But since we're talking about business, we're not going to use the variables x and y. Instead, we're going to be using quantity and price, so Q and P, as our variables. So what do we need to do with this? We need to take the information and figure out how to write it as a point. And so I'm going to just write the first point for you, and hopefully you'll be able to figure out how to write the other point. So what we need to do to think about this point is we have this relationship between the $10 per ticket price and the 1,000 seat quantity. So here, when we're thinking about this, we're manipulating the price. So price is our independent variable here. So we have 10, 1,000. So that's one of our points. You need to figure out a second point based on the information we have here, and then use that to set up a linear equation. And you can do it in y equals mx plus b first, and then switch over the variables, or you can start by using Q and P as your equation. That's fine. So you're going to find a linear equation, and then in part B, we're going to use our equation to substitute into the revenue function. Okay, So hopefully that sounds familiar from algebra. And then once we have that substituted into revenue, we are able to find maximum price, or the price and quantity that will maximize this function by using first derivatives. So we're not able to use derivatives until we have the equation in part B set up. But we can't set up the equation in part B until we set up the demand equation, which is the linear equation for part A. So there's a lot of pieces in this. A lot of it is algebra. So if it's been a while since you've done this type of algebra, you may have to really think about it or ask someone near you, which is totally fine. That's why we're doing this. But I want you to take about 3 minutes, see what you can figure out for these different pieces and see what you can come up with. And then we'll go through it together. All right, take about 30 more seconds. All right, so let's walk through the different steps of this, make sure we get everything set up and that we can apply what we've been doing to figure out how to maximize our revenue. So for the first step, we're trying to set up a linear equation that sets up for us what's called the demand function. And so the information we start with is that if we charge $10, we sell 1,000 tickets, right? We fill all 1,000 seats. We also know that for each additional dollar charged, the number of seats purchased is reduced by 50. So that means if we change this 10 to an 11, so one more dollar, that we have to subtract 50 from 1,000. So that's 950. So we have a second point here. And now we want to use this to get the equation of the line. So like I said, you can do this y equals mx plus b and then change the variables, or you can just start with the variables. I will start with y equals mx plus b just so we're clear where the things are coming from, and then I'll change the variables at the end. So to do y equals mx plus b, we're going to need a slope and a point. We have some points that we can use, but to get the slope, we're going to do the change in y over the change in x. Right, so we have 1,000 minus 950 divided by 10 minus 11. Okay, so that's going to give us a slope of negative 50. So in y equals mx plus b, we would have negative 50x plus b. To solve for b, we can plug in either one of our points. Doesn't matter which one we pick. So 10, 1,000, if we were going to plug that in, we would do 1,000 equals negative 50 times 10 plus b. This is negative 500. We would add that to the other side. And we get b equals 1,500. So our equation becomes y equals negative 50x plus 1,500. But now we want to turn this into the same equation, but using the variables that we need here, which are price and quantity. So I want you to look at one of these points. So we'll just pull out the 10, 1,000. Okay. Normally, we write a point x, y. But remember that 10 represented the price. So p, q. Which means that instead of x, we need to write p. And instead of y, we need to write q. So we have q equals negative 50p plus 1,500. So I just swapped the variables here. And as I mentioned, this type of equation is called a demand equation. Okay, it's called the demand equation because you're going to figure out what quantity will be demanded for a certain price, right? If we set the price at $10, then 1,000 will be demanded. If we set it at 11, 950 will be demanded. So this is called the demand equation. So that's part A, okay? For part B, it says, remember that revenue is price times quantity. So we start with that, right? So we've talked about that before. Revenue is the amount of money you take in from selling an item. And so we want to use our equation, that should say from part A, to set up the revenue equation by substituting in the demand equation in for P. Okay, you don't actually have to do it for P. You can do it for Q. Since we are going to look at price and quantity, I think I'm actually going to substitute it in for Q. If we just wanted to figure out what Q was, we would rewrite this equation in terms of P and substitute that in, but we don't actually need to do that here for this one since we're looking for both. So what does that mean? That means here, instead of Q, I'm going to substitute in what Q represents, right? So I P times, now I'm going to put in negative 50P plus 1,500, right? So this is my Q, right? So P times Q. So I can distribute algebraically this P through, so negative 50 P squared plus 1,500 P, okay? The reason why I need to substitute in for either P or Q into revenue is so that I only have one variable. So typically, price is fixed, right? We say, P is a constant. But when we have a demand equation, we are varying P. So we end up with two variables. So by figuring out the demand equation and substituting in, that reduces this to one variable. And we need it to be in terms of one variable in order to find critical points, which then allows us to find maximums. If we have two variables, we don't have the tools or techniques yet to figure out how to take derivatives with two variables. So that's why we're substituting it. So our next step now is to find the first derivative of this function so that we can find any critical points. So here The 2 comes down to multiply the 50. And I get negative 100p plus the derivative of 1500p is 1500. And we want to know, when does that equal 0? Okay, so we bring the 100p over, divide both sides by 100, and I get p equals 15. Okay, so at a price point of $15, I have either maximized or minimized revenue, right? But I want to make sure that it's actually a maximum. So I'm going to take a peek at the second derivative and use the second derivative test. The second derivative here is negative 100. If the second derivative is negative, the original function's concave down. So this does maximize. Now, for part C, it was to find the price and quantity that maximized. So in order to find the corresponding quantity, I need to go back to my demand equation and plug the 15 in. So here I have Q equals negative 50 times 15 plus 1500. And that's going to give me a quantity of 750. So when the price is set at $15, the quantity demanded will be 750 tickets, and that will maximize our revenue. Okay, so sometimes we also ask, what is that maximum revenue, right? Because that's another question that could be related to this. So if we wanted to know the revenue, we would just multiply the 15 times 750. And so even though this isn't the actual question, I'm just going to add it here to remind you. So if we multiply those two together, we would do 15 times 750, and that maximum revenue is $11,250. Okay, so that's your max revenue that you can make in this theater. You would charge $15. Charging $15, you would sell 750 tickets, and that would give you $11,250. Okay, there's no combination that's going to give you more. And even if you check our original combinations, right, like 10, 1,000, you may think, oh, if I sell all 1,000 seats, I'll make more money. But 10 times 1,000 is only $10,000. So by charging $15, we sell less seats, but we make more money. Okay, so whenever we're relating sort of prices and demand, this is the type of work we can do where we can bring in derivatives to maximize our revenue. Obviously, if we maximize our revenue, that will hopefully help us boost our profit. We don't know anything about the cost equation here, so we don't know for sure, but maximizing revenue typically is one strategy that a lot of companies use to then boost profits overall. Okay. All right, so that's the last example from the cost and revenue work. You will find on the homework that it's a lot of, maximizing revenue, maximizing profit, minimizing cost. And so when you see those words, maximum, minimum, you're thinking first step is first derivative equals 0. Then we're looking for critical points, and then using the critical points to determine, our maximum and minimum quantity or price, depending on what we're looking at. All right. So now we're going to shift gears and we're going to talk about global maximums and minimums. And I hinted at this a little bit when we started 4.1, but we didn't go into it too much. And I said, oftentimes when we think about maximums and minimums, we're thinking of like the biggest and smallest of something. And then we talked about why local maximums and minimums are different. But now we're going to go back and talk about global maximums and minimums, which are the biggest and smallest for a function. So what do we mean by biggest and smallest, right? That's what we have to sort of talk about and look at. So a global maximum, so we'll start with maximums. So a function is said to have a global maximum at some value p if f of p is greater than or equal to all values of f of x. So in this definition, we are talking about f of p, which is a y value. So what this definition is saying is if you have a y value that is larger than all other y values, then that is a global maximum. Okay, and a function is said to have a global minimum at some point p if f of p is less than or equal to all values of f of x. So if you have a y value that is less than all other y values, that's when you have a global minimum. So one of the things that I want to point out here is that our global maxes and mins are defined by their y value, right? By their dependent value. We are thinking about the up and down of the function, the highest point and the lowest point, and that's defined by the y value, okay? Functions, they only have one global maximum or minimum or no global maximum or minimum. You cannot have multiple global maximums or minimums, but they can happen at multiple places. So if the highest y value you have is 5, that is your global maximum. But you could get to 5 at x equals 0, x equals 2, x equals 7. That's fine, but there's only one y value that is the highest. And that's how we talk about global values, by their y value. Okay, so what does that look like sort of on a picture? So as a reminder, let's label our local maximums and minimums. So local maximums and minimums happen when we have horizontal tangent lines. And we can have multiple of them because it's the highest or lowest in a small area, okay? When we look at global maximums and minimums, we are looking at the highest point, which is here. This is the global maximum. And the global maximum here is 2, because again, we define this by the y value. And then the global minimum is over here. This is the lowest. Okay, and this looks like it happens at y equals 0.5. And so I want to draw your attention to where these things happen. So let's start with the global minimum. The global minimum happens at a critical point. Okay, whereas the global maximum happens at an end point. Okay, it turns out that when you are looking for global maximums and global minimums, that these are the two places we need to check, okay? So we need to check what's happening at end points, and we need to look at what's happening at critical points. So those are the two places where we can have global maximums and global minimums, okay? So our process for this is if we know we are looking for a global maximum and global minimum, we start by finding the critical points. Once we have critical points, we make a list of all critical points and all end points that are given to us for the function. We then plug each of those values back into the original function to compare the y values. One thing we need to be extra careful about, however, is that if we are given an interval, which we are probably 75% of the time, we can only use critical points if they are on that interval. So if I say you have to be between 0 and 10, and you have a critical point at -4 and 4, you can only use the +4 because that is the one that is on the interval, okay? So let's try this with an example. I lost my index card here. Let's cover up the other ones here. So we want to find the global maximum and minimum of the function x cubed minus 9x squared minus 48x plus 52 on the interval -5 to 11. So I'm going to write this function a little bit bigger just because it looks small to me on the screen. Okay, so what do we need to do? step one, we need to find critical points. One, critical points. Okay. Step two, we're going to make a list. And on our list, we're going to have critical points and end points. Where do we get the end points? We get them by this interval where we are defined. That's why we have less than or equal to and greater than or equal to. So we make a list of all our critical points and end points. Again, the critical points have to be on the interval. And then step three, we test those points in the original function. Okay, because we are looking to see which one has the highest and lowest y value in the original function. Okay, so let's try this out. I'm going to give you 2 to 3 minutes. So step one, find the critical points, find the first derivative, find when it equals 0. Step two, make a list of critical points and end points to be tested. Step three, plug those values back into the original and determine which one is the highest y value and which one is the lowest y value. Okay, try it out and then we'll go through it together. All right, take about 30 more seconds. All right, so let's walk through this process and make sure that all the steps make sense here. So step one, we need to find critical points. Okay, so we're going to start by finding the first derivative of our function. So we have 3x squared minus 18x minus 48. We want to know when does that equal 0. So I factored this. So again, you can factor it or you can use the quadratic equation, whichever you prefer is totally fine. but I have 3 times x minus 8 times x plus 2 equals 0. So that tells me I have critical points at x equals 8 and x equals -2. Okay. So once I have my critical points, I need to check to see if they exist on the interval I'm given. So for this one, I'm given that the interval is going to be between -5 and +11. So both of these numbers are between -5 and +11, so I can use them. So now I'm going to go ahead and make a list of all my critical points and all my endpoints. So here the order doesn't really matter. So we have x equals 8, x equals -2. Those are my critical points. And then -5 and 11. Okay, so that's what my list looks like. And what I need to do is I need to plug each of these back into the original to see what I get for a y value. Okay, so I did that on my calculator. When I plugged in 8, I got -396. When I plugged in -2, I got +104. When I plugged in 11, I got -234. And when I plugged in, oh, that was 11, -234. And when I plugged in -5, I got -58. Okay. So the reason we make this list is because, again, global maximums and minimums are defined by their y values. So I have to look through this list and ask on a number line, which one is the biggest and which one is the smallest. Okay. So y equals 104 is the biggest. So I have a global max is 104. And then I also need to ask which one is the lowest on the number line or the smallest. And so my global minimum here is -396. Okay. And so I really want to stress how we talk about this. When you're asked for the global max, it's 104. It's the y value. When you're asked for the global min, it's -396. It's the y value. Sometimes on the homework, it'll say the global maximum happens at x equals what? So if we were looking for the global max and it said happens at x equals, then you'd fill in the -2. That's where it happens, but the actual global max is 104. So if it says, what is the global maximum? You would say 104. Okay, hopefully that makes sense. So that's what our process looks like, right? Those are the steps. Find critical points, make a list of critical points and any endpoints, and then test them in the original. So we're going to try a couple more examples of this just to get used to the process. And then we'll look at some ways that this can sort of vary and other ways we may ask about global maxes and mins. Okay, so we're going to look at 2 problems here that are both algebraically based that are going to use the same process that we just looked at. The first one is talking about the number of eggs hatching. We want to find the temperature T at which the largest number of eggs hatch. So again, we're looking for, in this one, we're looking for the global maximum, but we're actually looking for the T. So we're looking for the independent variable, so like the X, but here we're looking for the T. But the process is the same. We have to compare the dependent values. And then for 3, same process, but now our function is a little bit harder. So I'm going to just write it a little bit bigger because, again, it's looking a little small on my screen. So this is x over x squared plus 1, right? So similar to the problem we just did, only the function now, hopefully you recognize we're going to need to use a quotient rule, okay? So I want you to try these out, do the same process, and once you have your list of y values or dependent values, I want you to think about how you can best answer the question as it's presented. Okay, I'm going to give you 5 minutes to try out these 2 problems. You can do them in either order. So if you want to try this one first because you're feeling really good about the quotient rule, that's fine. But try them both out, see what you can figure out, and then we'll go through them together. All right, take about 30 more seconds.
Does anyone have any questions at the moment? We wait like 2 or 3 minutes till she comes back, and then I really don't know what happened. One thing I will say with the global maximum, the global rules, it's really important that you check the endpoints.
Did she disconnect?
Yeah.
Okay, all right.